3D Scatterplot Navigation. Harald Sanftmann, student member, IEEE, and Daniel Weiskopf, member, IEEE Computer Society. Abstract. For 3D scatterplots, we present an interpolation and projection technique that supports the smooth exchange of one or two data dimensions at a time. Even though this exchange can be considered as a rotation in 4D or 5D data domains, we guarantee that the projection to image space is perceived as a 3D rigid body rotation, with a consistent motion of the data points. We conducted a controlled user study showing that 3D rigid body rotations outperform direct transition between scatterplots. We further extend our technique to support navigation between 3D scatterplots by introducing 3D scatterplot matrices. The usefulness of our approach is demonstrated by application examples, including a case study with a natural language processing expert. Index terms, visualization, scatterplot, multidimensional data, coordinated and multiple views. See Cedilla 1I. Introduction. C. Transition between 2D scatterplots helps preserving context. This benefit has been observed before and successfully applied to the navigation between arbitrary 2D projections and to 2D scatterplot matrix navigation for multivariate data visualization. In this paper, we address the navigation between 3D scatterplots, especially in the context of a novel 3D scatterplot matrix navigation method. A key feature of our technique is that it facilitates interpolation between arbitrary 3D scatterplots as long as one axis mapping is preserved. The techniques mentioned above for 2D scatterplots share one interesting property. The motion of points during the transition from one view to another looks like a 3D rigid body rotation. This greatly helps in tracking the motion of points. However, most of the 2D projections lose this advantageous property when directly extended to 3D scatterplot interpolation. We address this issue by deriving a set of projections guaranteeing that the interpolation appears as a 3D rigid body rotation. We conducted a controlled user study with 12 participants, showing that our new 3D rotation approach is significantly better than direct animation between scatterplot views for perceiving the correspondence of points in different scatterplots. We also demonstrate the usefulness of our approach for a typical application. The example is an application in natural language processing, where explorative data analysis with navigation in 3D scatterplot matrices is useful for developing feature extraction methods. 2. Continuous B background 2.1. Scatterplot navigation 2D. Scatterplots and scatterplot matrices are widely used in multivariate data analysis and provided by different software products like Prim99, XMDV Tool 27, Polaris 19. The authors are with the Visues, University of Stuttgart, Almendring 19, Stuttgart 70569, Germany. Email sanftmann@gmx.net, Weiskopf@visues.unistuttgart.de. Manuscript received August 19, 2011, revised December 30, 2011, accepted 8 January 2012, published online January 27, 2012, recommended for acceptance by S. Takahashi. For information on obtaining reprints of this article, please send email to tvcg@computer.org and reference EEX log number TVCG 2011-080192. Digital Object Identifier number 10.1109/TVCG.2012.35, 1077 to 2626/12/$31.0 sharp S, 2012 IEEE Gobi 20, or Gobi 21. This section covers previous work related to explorative multivariate data analysis with scatterplots and classifies the techniques according to the taxonomy of Table 1. This table reveals white spots addressed in this paper, indicated by here in the table. We differentiate the techniques according to the number of axes and viewport interaction possibilities, viewport in the table, and the axis mapping, axis mapping. 2D scatterplots, 2D, have two, usually screen-aligned, axes assigned to different data dimensions and no viewport interaction in sense of rotation. In contrast, 3D scatterplots, 3D, display three data dimensions assigned to three orthogonal axes. The third dimension allows for 3D user interaction, with 2 or 3 rotational degrees of freedom to change the viewport. Since computer screens present a 2D image, 3D structure need be conveyed by depth cues such as structure from motion or occlusion, which are easily supported by 3D scatterplots. Even for 2D scatterplots, occlusion can be implemented by using another data dimension for depth sorting, 2D plus sorting. The latter can also be compared to a full 3D scatterplot, where the only difference is the missing rotational interaction in 3D. This mapping also requires 3 axes, 2 for spatial position and 1 for sorting. More flexibility in data mapping is introduced by extending the fixed mapping between certain data dimensions and scatterplot axes, fixed in the table, to a flexible exchange of mapped dimensions, either by swapping the dimensions of 1 or 2 axes, swap, or by manipulation of dimensions, manipulation. Prim 99 allows one data axis to be manipulated at a time, whereas Gobi 21 allows manipulation of both axes in its two-to-tour. While interacting with the scatterplot in Gobi, the motion of the points can be perceived as 3D rigid body rotation. However, in contrast to our technique, just one data dimension can be actively manipulated at a time. The other data dimensions change accordingly to maintain a valid projection by staying in a plane orthogonal to the manipulated dimension. Additionally, points are not sorted according to a third axis, but simply drawn in the order they are defined. This is not an issue if the points are drawn in one single color, but if more colors are used, 3D perception can suffer because the depth perception from the kinetic depth effect may be overridden by the depth cue from occlusion that can be detected from the differently colored points. With our technique, we always use a third, published by the IEEE Computer Society 1970. Table 1, Taxonomy of Scatterplot Techniques for Multivariate Data Analysis. Methods with mapping transitions that appear as rigid body rotations are underlined. Combinations that are not in focus of the specific technique are in brackets. Axis that is consistent with the motion of the points to support 3D perception. Furthermore, we guide the user by using 3D scatterplot matrix navigation. With the Grand Tour 1, 2, GT, the user is presented a sequence of projections that come arbitrarily close to any 2D scatterplot projectable from the multidimensional dataset, with smooth in-between transitions. However, there is no user interaction involved. The axis mapping changes all dimensions during transition, and rigid body motion is not ensured when interpolating between projections. Yang 29 applied the Grand Tour in 3D GT. Finally, Elmqvist et al. 8 guide the user in navigating between 2D scatterplots by changing one axis mapping at a time with their rolling the dice, roll dice method. Each of the axes shows one data dimension before the transition and one dimension after the transition, but the mapping of one axis is swapped during the transition. Our navigation approach extends their technique by using 3 axes and supporting the swap of 1 or 2 axes during transitions. The main difference between the manipulation and swap approaches, besides the interaction methods, is the way in which dimensions can be assigned to the axes. The swap approaches only assign one data dimension to each of the axes, respectively, except for the transitions, which serve only as a context-preserving mechanism. Interpretation does not take place during transitions, whereas the manipulation approaches assign a linear combination of dimensions to the axes. Because of this more general mapping, the projections that can be generated by manipulation approaches are a superset of the projections producible by swap approaches, but interpreting linear combinations of dimensions is much harder. 2.2 Perception. There is the general notation that 3D graphics is problematic for typical diagram techniques in information visualization due to inherent issues related to spatial perception and occlusion. We share this general point of view, but would like to make the case that there are certain applications and configurations where the advantages of 3D outweigh its disadvantages. One recent example is given by Dang et al. 6, who show how stacking graphical elements in the third dimension overcomes serious problems of color coding in 2D plots. In our scenario, the perception of 3D objects and motion perception play equally important roles. Animation is employed to convey correspondence between dots that represent the same data point in 2 different scatterplots, following the principle of Elmqvist et al. 8. However, animation itself should be used with caution as a means of graphical representation, as discussed by Tversky et al. 25. They show that, in general, animation can be useful when it follows the principles of congruence and apprehension, which implies that similar transitions should be grouped. 12. We follow this general approach and apply it to low-level perception by employing animation in the sense of structure from motion processing, where perception of motion is tightly and effectively linked with spatial perception. Early work by Oman 26 describes a computational approach to derive 3D structure from motion on screen. It contains a constraint for the interpretation of structure from motion, which he calls the rigidity assumption. In particular, he proved that the 3D structure as well as the motion can be calculated given at least 4 points in at least 3 views. His experimental findings indicate that the human visual system uses a similar computational approach. As summarized by Ware 28, numerous subsequent works showed that structure from motion indeed is a strong depth cue, more powerful than stereoscopic depth. We rely on low-level perceptual processing to extract 3D structure from motion, as summarized by Todd 23, and use it for effective perception of moving 3D objects made of points in scatterplots. If animation was used in a 2D setting for scatterplots and two-axis mappings were changed simultaneously, data points would have to move on trajectories that differ from those of 2D projections of a single 3D rigid object. Therefore, these points would move in a quite incoherent manner. Although tracking of multiple objects is possible, 17. The number of objects is limited to a small number, around 5 objects, however very much dependent on the application. See the overview paper by Kavanagh and Alvarez. 3. The perception of a single 3D rigidly moving object is associated with much less cognitive load than the independent motion of 2D points. This is the key observation and motivation for our work. The perception of correspondence between scatterplots is best supported by animation with coherent rigid body motion. 3D scatterplots have been employed at various places mainly because they provide one additional data dimension and reduce information loss. 16. However, often the 3D nature of the internal representation of the data is provided to the user only by the ability to rotate the viewport to generate new projections on a 2D screen. 4. This is a quite unsatisfactory representation and it is not desirable. The interaction necessary to explore the 3D scatterplot should be minimized by providing depth cues in the 3D scatterplot rendering. First improvements to the spatial perception of 3D scatterplots were proposed by Donahoe et al. 7. Like adjusting point size based on depth and stereopsis. The use of stereographic depth in a cave environment was presented by Yang, 29. Other improvements are the use of brushing and linking, with additional graphical cues for halos or depth-oriented color coding, 15, or illumination in dense plots, 18. In a quantitative study, Poco et al. 16 showed that 3D scatterplots outperform 2D scatterplots in terms of finding neighboring clusters to points, but they also found out that 3D interaction is more difficult and more time-consuming. One serious drawback of 3D scatterplots, when using perspective projection, is the fact that the position of a point in the data domain cannot be accurately estimated based on its screen position, since the screen position varies with the depth value. We intentionally do not use perspective projection as to make the scatterplots look like 2D scatterplots when viewed along the major axes. From such 1971 static viewpoints, without interactive rotation, we have no disadvantages from 3D but only benefits. We retain the advantage of a depth axis that provides depth sorting. This depth information is conveyed to the user through occlusion and is enhanced by the halo rendering technique we present, but do not have any negative impact of 3D. 3. Interpolation scheme and peak rejection technique. This section presents our interpolation scheme and projection technique that enable the transition between 3D scatterplots. We assume that the scatterplots share one common data axis. Then, our technique guarantees that the transition is perceived as a 3D rigid body rotation. 3.1 Interpolation Scheme. The interpolation scheme is used to interpolate between different 3D scatterplots. Mathematically, our interpolation scheme is a projection with one interpolation parameter which projects from the original m-dimensional data domain to 3D space as formulated by a generic projection M, IRM. IR3. Without loss of generality, we start following projection. F21000 M0 and 1/44010000010 are transitioned from the 0003, 5. In one case, only one of the dimensions needs to be changed. Without loss of generality, we consider the transition to the following projection: 2300010 M0, M1 and 1/4401000, 5, 00100. In the other case, two of three dimensions need to be changed. Here, we consider the transition to the following projection: 2300010 M0, M2 and 1/440100000, 5, 00010. We want a smooth transition between the 3D scatterplots. Therefore, we define the transition parameter, interpolated between 0 and equals 2, and use 1 and 2 to interpolate the positions of the points 2, 3 cos 00 sin 0, T1 and 1/4401000, 5. F1 thorn 00100, 2T2 3 cos 00 sin 00, 1/440100000, 5, 00 cos 0 sin 0, F2 thorn. The interpolation defined by 1 performs the transition equals 2 from M0 to M1. Proof: TO1 and 1/4 M0 and T1 and 1/4 M1. The interpolation defined by 2 performs a transition from equals 2M0 to M2. Proof: TO2 and 1/4 M0 and T2 and 1/4 M2. As an example, consider the point P in the m-dimensional data domain and let Pi be the ith component of P. We perform a change of one dimension by using the transition T1. During the transition, P is projected to the point Q in the 3D scatterplot. Q 1/4 T1, P 1/4 1/2 P1 cos thorn, P4 sin, P2, P3 T. The transition starts at 1/4 0, where Q 1/4 1/2 P1, P2, P3 T, and ends at 1/4 equals 2, where Q 1/4 1/2 P4, P2, P3 T. From the trigonometric expressions in the coordinate functions of Q, it becomes clear that the point does not simply move on a linear path from the one position to the other with constant velocity during the transition. 3.2 Projection Technique. The interpolation scheme presented above ensures that we can interpolate from one 3D scatterplot to another, but it does not guarantee that the transition looks like a 3D rigid body rotation. We now show that there are projective transformations that make our interpolation scheme look like a 3D rotation of a rigid body after projection to the image plane. Let PZ be the orthogonal projective transformation that projects to the Z 1/4 0 plane 23100, PZ 1/440 105 000. This projection operator is applied to model the projection to 2D image space. Furthermore, RU denotes the rotation around the U-axis in IR3 with angle. Our interpolation schemes, T1 and T2, together with the following projective transformations, are equivalent to a rigid body rotation of points x2 IR3, with the angle around the y-axis, followed by the projective transformatine PZRZ, x1/4 PZRZRYX, the Theorem 1. The interpolation scheme T1 followed by the projective transformation PZRZRX is equivalent to the rigid body rotation followed by the projection in 3, PZRZRX, T1D 1/4, PZRZRYX. Equivalence is defined as follows. For fixed and for each data item in the high-dimensional vector space D, there exists a point X for which the equation holds for all 2 IR. Theorem 2. The interpolation scheme T2 followed by the projective transformation PZRZRY is equivalent to the rigid body rotation followed by the projection in 3, PZRZRY, T2D 1/4 PZRZRYX. Proofs of theorems 1 and 2 are provided in section 3.3. Theorems 1 and 2 state that there are 2 degrees of freedom for the selection of the projection, and Since general rotations have 3 degrees of freedom, 1 degree of freedom is lost in our case, restricting the possible class of projections. The parameter describes a rotation in the image plane around the viewing axis. Since is interpolated from 0 to equals 2, the user will perceive a corresponding 90-degree 1972 rotation around the y-image axis, rotated by in the image plane. If one axis changes, Theorem 1 implies that the other degree of freedom is perpendicular to the rotation direction during the interpolation because describes a rotation around the x-axis prior to the rotation with. If 2 axes change, Theorem 2 indicates that the other degree of freedom is identical to the rotation direction during interpolation because describes a rotation around the y-axis prior to the rotation with. The practical implication of the above mathematical consideration is as follows. For consistent 3D rigid body rotations, we cannot start from any orientation of the initial 3D scatterplot and then make a transition to any target 3D scatterplot. In fact, the data dimensions to be exchanged during transition dictates restrictions to axis orientations, in the sense that they defines the subspace of view directions from where the dimensions exchange will look like a rigid body rotation. In the case one axis mapping is changed, the changing axis needs to lie in the image plane, and in the case 2 axes are changed, the non-changing axis needs to lie in the image plane. One navigation approach could then perform an automatic view adjustment in the application while navigating between 3D scatterplots, ensuring that the restrictions of axis orientations are met. An alternative approach leaves the snapping to valid start orientation to the user. The projection to the image plane PZ simply maps the depth component to 0. This implies that the depth component is not important at all, and this is the case for the kinetic depth effect. However, as mentioned before, providing additional depth cues when visualizing 3D data on a 2D screen is important for shape perception. Our 3D scatterplot renderer uses occlusion and halo rendering to convey depth information. Therefore, not only the 2D screen positions of the points need to be consistent to the rigid body rotation, but also the depth of the points prior to projection. The depth value consistent to the rigid body rotation is given by the z component of RZ/RYX. See section 3.3 for the calculation of x. Theorems 1 and 2 do not state that there is only one rigid body that is consistent to the point movements. In fact, there is another interpretation of this interpolation and projection, with x 1/1/2xxxyxzt. This PZRZRY T2D 1/4 PZRZRYX reflects the fact that given the orthographic projection, one cannot differentiate if one rigid body is rotated in one direction or a corresponding other rigid body is rotated in the opposite direction. However, using additional depth cues, we make the interpretation unambiguous. Thus, with 2 cos RZ RY, 1/4 4 cos sin cos 0 3 sin cos sin 5 cos, and x 1/4 x cos y sin thorn z sin cos, y 1/4 x cos sin thorn y cos thorn z sin z 1/4 0 2323x x 6767, where 4 years 5 1/4 x and 4y 5 1/4 x zz. First, we consider the T1, then the T2 interpolation. Theorem 1, see section 3.2. Proof. Let x 1/4 PZRZRXT1D. In the following equations, we set 1/4 cos and 1/4 sin, 2 3. 0 0. RZ RXT 1 1/4 4. 0 0. 5. 0. 0 0 0 leads to x 1/4 D 1 cos D 2 cos sin thorn D 3 sin thorn D 4 sin cos, y 1/4 D 1 cos sin thorn D 2 cos D 3 sin cos thorn D 4 sin z 1/4 0. We obtain x 1/4 D1, y 1/4 D2 cos D3 sin, and z 1/4 D4. UT Theorem 2. See section 3.2. Proof. Let x 1/4 PZRZRYT2D. Then, 2RZRYT2. 1/4 4. 0. 0. 0. 0 3 5 leads to x 1/4 d 1 cos d 2 sin thorn d 3 cos thorn d 4 sin cos thorn d 5 sin cos y 1/4 d 1 cos sin thorn d 2 cos thorn d 3 cos sin thorn d 4 sin cos thorn d 5 sin 3.3 proofs. We will show that our interpolation schemes, T1 and T2, together with specific projective transformations, are equivalent to a rigid body rotation of points x2 ir3 with the angle around the y-axis, followed by the projective transformation PZRZ x 1/4 PZRZRYX. Z 1/4 0. We obtain x 1/4 d 1 cos thorn d 3 sin, y 1/4 d2, and z 1/4 tu d 4 cos thorn d 5 sin. 4. User study. We conducted a user study to evaluate the effectiveness of our 3D rigid body rotation approach and to compare it to the direct transition between scatterplots. We consider the more problematic of the two situations. Two axes are changed. Our research question was the following: should we first rotate the camera to a subspace where the consecutive transition 1973 deficiency, which we confirmed by an Ishihara test and a Snellen chart to estimate visual acuity, Figure 1. Scatterplot, showing synthetic data used during the user study, presented from the initial viewport, will look like a rigid body rotation, or should we perform the transition directly from the actual viewpoint without rigid body behavior? Our hypothesis was that 3D rigid body rotation would allow users to identify correspondence between elements in the scatterplots with less error than when direct transition was performed. 4.1 Task and Stimuli. The participants had to identify corresponding clusters from a multidimensional dataset shown in scatterplots before and after the transition. The synthetic datasets were generated from the same random distributions and contained 10 clusters. The number of clusters was chosen to be larger than the typical number of objects that can be tracked independently, C3. Each of the clusters consisted of 50 points from a normal distribution. The cluster centroids were uniformly distributed in the domain. To add a degree of distraction, we also added 100 uniformly distributed noise points over the domain. Figure 1 shows an example with color coding of the clusters. For the direct transition case, the initial scatter plot was shown for 4 seconds. Then, the points were rendered gray and a transition was performed that changed the axes 0 and 1. This transition took 1.83 seconds, 110 frames at 60 FPS. After the transition, a single cluster was highlighted and the user had to select the corresponding cluster from a second scatter plot drawn next to the animated one showing the initial plot. The selection process had no time constraints. The result of the selection was recorded for the subsequent analysis of the study. The rigid body rotation task was similar. The only difference was that we applied a rotation to align the axes 0 and 1 with the x-axis of the screen by performing a 10-degree rotation within 0.33 seconds, 20 frames, prior to the transition, which we shortened to 1.5 seconds, 90 frames. By this alignment, the transition looked like a 90-degree rigid body rotation, and the overall duration was identical to the direct transition task. 4.2 Participants. We performed the study with 12 participants, 7 male, 5 female. The participants were students of our university. 6 were computer scientists, 6 were engineers. The average age was 26, minimum 21, maximum 32. They were paid 1/4 C10 for participating in the study. 6 stated that they were familiar with visualization techniques or had attended a lecture with this topic. All participants had normal or corrected to normal vision without color vision. 4.3 Study procedure. The study was conducted in a laboratory that was insulated from outside distractions. We used a 22-inch BenQ G2200WT TFT screen at a display resolution of 1:681:050 pixels with 24-bit color depth driven by a Windows PC. Subjects were introduced to the methods and had time to gain experience and develop strategies to solve the tasks. Feedback was given in terms of right or wrong choice they made. This training phase took about 15 minutes. After the training phase, they had to perform 100 tasks with both methods without feedback. The same set of 100 different pseudo-random synthetic data sets was generated for the two methods. The same starting camera position was used for rotation and direct transition, and the ending position differed only by 10 degrees. This repeated measures design had two within subjects variables, method, i.e., direct transition versus rigid body rotation, and dataset, i.e., the different datasets. Since we were not interested in the differences in difficulty of the datasets, we randomized and balanced the method variable but not the dataset variable between subjects, minimizing the order effects on the paired samples. Switching randomly between the methods after each task would have been quite demanding for the participants. Therefore, we decided to group the tasks of the same method. The participants were randomly assigned to start with the rotation or the direct transition tasks. To further minimize learning effects, we split the 100 tasks in two parts and replaced the ABBA/BA sequence by an ABAB/BABA sequence, where A and B correspond to direct transition and rigid body rotation, respectively. Our test procedure was similar to a crossover design with 2 periods and 2 treatment sequences. One round of A or B took about 10 minutes, leading to an overall average study duration just below 1 hour per participant. 4.4 Study results. From the complete set of 12 100 tasks, there were 198 cases where direct transition performed better than rigid body rotation, and 251 cases where rotation was better. In 308 cases, both were correct, and in 443 cases, both were wrong. An often used descriptor for success in Bernoulli experiments are the odds direct Thorn 1/4 Eth 198 Thorn 308 Thorn equals Eth 1200 198 308 Thorn 1/4 0:729. Odds Rot Thorn 1/4 Eth 251 Thorn 308 Thorn equals Eth 1200 251 308 Thorn 1/4 0:872. And the odds ratio comparing the odds of succeeding the tracking of the cluster for using the rotation method with the odds of using the direct transition method is R-Rot. Direct 1/4 odds Rot Thorn equals odds direct Thorn 1/4 1 to 196. That means the odds of succeeding with the tracking are 19.6% higher for the rotation method than for the direct transition method. We modeled the experimental variables method and dataset, their interaction method dataset, and the main effect of subjects. A simple ANOVA cannot be applied in our case, since the error component cannot be assumed to be normally distributed. Instead, we used logistic regression, which is a generalized linear model, 14, to account for the binomial distributed outcomes. The likelihood ratio test showed that method was significant. 2 Eth 1 Thorn 1/4 5:80 1974. P 1/4 0:016. There was no significant interaction between the method and dataset variables. We also analyzed learning or fatigue effects. The variance captured by the dataset consists of 2 parts. One is the difficulty difference between the tasks, the other is the learning effect. Since the tasks were generated randomly, we assumed that task difficulty was independent from task ordering. To analyze the effect of learning or fatigue, we used the task ordering as additional effect in the regression to separate the learning effect from the randomized difficulty. Therefore, we modeled a linear dependency on the task or DARE variable, an integer variable that describes the ordered index of the task for a participant, which is an additive effect on the log of the odds in the logistic regression model. The estimated parameter for the task order was task order 1/4 0:0028, log of the odds between consecutive tasks, which is a positive learning effect and corresponds to an increase of correctly identified correspondences of 6.9% points during the 100 tasks. The likelihood ratio test on the task order was significant. 2 Eth 1 Thorn 1/4 391, P 1/4 0:048. 4.5 Discussion. The main result of the user study is that rigid body rotation is more effective than direct transition by unconstrained interpolation between scatterplots. Another result is that there are learning effects for both types of transition schemes. We conjecture that the learning effect is caused by the fact that the participants were no expert users of 3D scatterplots. Therefore, we expect that the overall performance of 3D scatterplot navigation will further improve with increasing experience. 5S Scatterplot Matrix N Navigation 5.1 Technique. The technique presented in this section fills the white spots in Table 1 labeled with "Here" and can be seen as the 3D extension to the 2D scatterplot matrix navigation technique by Elmqvist et al. 8. Our interpolation scheme and projection technique can be used to navigate between arbitrary 3D scatterplots as long as one axis mapping is preserved, and therefore are ideally suited as key components in our novel 3D scatterplot matrix navigation. Unlike in the original approach for 2D scatterplots, the transitions would not automatically look like 3D rotations, and special viewpoints need to be set, limiting the two rotational degrees of freedom, no angular rotation, to 1. Given an n-dimensional dataset, there are n2 2D scatterplots that can be arranged in a scatterplot matrix. For the extension to 3D, there are n3 3D scatterplots that can be arranged as n 3D scatterplots within a cube. However, such a presentation would suffer from occlusion, and selection of a 3D position, picking, would be cumbersome with a 2D input device. We want to apply our interpolation scheme to navigation limited to changes of 1 or 2 axes. Therefore, full 3D navigation is not necessary. By keeping one specific axis constant, we can reach n 3D scatterplots. Hence, there are 3 n 3D scatterplots that are reachable by changing at most 2 axis mappings from a given scatterplot. Not all of these are different. We display all scatterplots that preserve at least one dimension. Figure 2. 3D scatterplot matrix showing the 8D olive oil dataset. The X, Y, and Z axes are annotated with red, green, and blue colored numbers, respectively. The currently selected 3D scatterplot is marked with yellowish strips and maps the data dimensions 4, 3, 5 to the X, Y, Z axes. Plots to which one can navigate are marked gray. In the lower left corner, a widget shows the magnification of the plot under the current mouse position. A biplot 11 is included in the upper left corner. Scatterplots that preserve the dimension mapped to the x-axis are projected to the back face of the cube in x direction. The y and z directions are handled accordingly. In total, 3 2D scatterplot matrices are arranged on the back sides of a cube. We name this representation a 3D scatterplot matrix. Like a 2D scatterplot matrix can be used to navigate between 2D scatterplots, our 3D scatterplot matrix can be used to navigate between 3D scatterplots. Figure 2 shows an example of a 3D scatterplot matrix. Here, data dimension 3 is mapped to the y-axis, and all 2D projections of the 3D scatterplot matrices that preserve the y-axis mapping are projected to the back face perpendicular to the y-axis of the cube. Cf. the upper right part of the figure. This mapping from 3D to 2D is reminiscent of the EXO-VIS method, 24. This approach allows us to represent all reachable 3D scatterplots by their 2D projections without overlap and occlusion. Therefore, elements can be readily selected by a 2D input device, i.e., just by clicking on the desired destination with a mouse. The selected element in the 3D scatterplot matrix is used as target 3D scatterplot for the transition. The interpolation scheme, presented in Section 3, is used to perform the transition in the 3D scatterplot view. The projection technique can be used to first rotate the view into a subspace where the transition looks like a rigid body rotation. In the current implementation, this is done by a user trigger but can also be done automatically prior to the transition. The rotation of the 3D scatterplot matrix is linked to the 3D scatterplot view. Therefore, the 2D scatterplot projections look like the main 3D scatterplot when looking along one of the major axes. The 3D scatterplot can be rotated by dragging with the mouse or by shortcuts that bring the scatterplot axes in alignment with the screen axes and provide views that are identical to 2D scatterplot views with the additional depth sorting. 3D scatterplots allow us to map 3 data dimensions to the axes of the plot. It makes no sense to map identical dimensions to different axes. Likewise, the utility to move an already mapped dimension to a different axis is limited. It may be easy to see such configurations in 2D scatterplot matrix navigation. It is easy to miss them in 3D navigation. To help the user find the remaining, appropriate axis mappings, we restrict the navigation to these mappings and mark them gray in the 3D scatterplot matrix, Figure 2. Dense scatterplots suffer from overplotting. See the upper image in Figure 4. This issue can be alleviated to some extent when using 3D scatterplots, to be more precise, 2D plus depth sorting according to our taxonomy. As mentioned in Section 2.2, depth cues are important when presenting 3D data on a 2D screen. By using the depth component for sorting and rendering halos around the points 15, we obtain more information from the 2D image. Naive drawing of halos around each point has also limitations in high-density areas 18. However, edge cueing techniques 22 for molecular visualization can be adapted to 3D scatterplot visualization. We implemented the edge cueing technique with a slight modification of the naive halo rendering. We apply a backward translation to the OpenGL projection matrix while drawing the halos. This renders halos just at significant depth discontinuities and facilitates shape perception. See the center image in Figure 4. 5.2 Applications. Here we present two application examples of our scatterplot matrix navigation technique. 5.2.1 Illustrative example of 3D scatterplot matrix navigation. We use the olive oil dataset to demonstrate 3D scatterplot matrix navigation because this dataset is well known and has a medium number of data items and dimensions. The dataset consists of 572 olive oils coming from 3 regions of Italy. The composition of each oil with respect to 8 fatty acids, palmitic, palmitoleic, stearic, oleic, linoleic, linolenic, arachidic, and eicosanoic, is given as data attributes. Figure 3 illustrates how scatterplot matrix navigation can be used to explore multivariate datasets by showing several steps of a navigation example. Given the goal of separating the 3 clusters, the task can be decomposed to first separate one of the clusters from the other 2, using one dimension of the scatterplot, and then the other 2 clusters from each other using 2 other data dimensions. This is not a new finding, 5. However, this example shows how the 3D scatterplot matrix navigation can be used to systematically navigate toward a 3D scatterplot in which the clusters are separated. The 2D scatterplots presented in the 3D scatterplot matrix help identify interesting 3D scatterplots that can be used as targets for next transitions. Separating clusters is just one possible, yet typical application. In general, our technique allows the user to obtain a preview of a target scatterplot, which helps in exploring a dataset. 5.2.2 Feature extraction for natural language processing. This application scenario covers the exploration of multi-dimensional data with many data points so that a dense coverage of scatterplots can be expected. More specifically, a 1975 domain expert from the field of natural language processing used our system and provided feedback. In the case studied, the expert user wanted to apply some novel feature extraction methods and develop new features for the PAN plagiarism corpus, PAN PC09, http://www.webis.de research/corpora. The derived dataset is 11D and contains over 1 million items, most of which are classified negative and a few of which are classified positive. The expert was familiar with the multidimensional analysis tool GOBI, but could not open such a large set with the application. Therefore, he was interested in using our application for analysis. Figure 4 shows dense scatterplots of the dataset. We first offered just 2D scatterplot matrix navigation to the expert by disabling the third axis and fixing the rotation of the viewport, which was similar to the technique by Elmqvist et al. 8. By looking at the scatterplot matrix, it became obvious that the 8 features, topls1, topls8, are nearly identical. The scatterplot navigation was found useful because the domain expert saw in advance where he would arrive after performing a movement, in contrary to GOBI, where navigation is more cumbersome because there is no preview. After the 2D session, we asked if he had missed a third dimension, but he answered that 2D was right for him. We then continued with the study and enabled the third dimension. The expert found the 3D scatterplot more informative than the 2D plots because he got an impression of the density of the points due to our halo technique. He found out that the red points have a high density and have a quite sharp border. He also found the 3D scatterplot quite useful because the additional data dimension and the easy navigation through rotation. The data dimension length _squared was mapped to the x-axis of the plots shown in Figure 4. Obviously, this quantity should not be negative. Furthermore, we see from the point distribution, especially when looking at the 3D scatterplot augmented with halos at depth discontinuities, that the plot on the right side at the maximum length _squared values matches the distribution on the left side at the maximal negative length _squared values. This may lead us to the hypothesis that the dimension length _squared was stored as an unsigned number that was interpreted as a signed one during processing. However, when we look at the bottom of Figure 4, we see that the pattern does not stop at length _squared equals 0, and we can conclude there must have been an arithmetic overflow during processing. This example demonstrates the additional information that can be obtained from 3D scatterplots compared to 2D scatterplots, even on a 2D output device, when we use techniques that are able to give an impression of 3D shape. According to our taxonomy presented in Table 1, it is obvious that none of the techniques presented in the 2-axis column are capable of revealing this 3D shape since they miss a depth axis. 6. See occlusions in future WORK. We have presented an interpolation scheme and projection technique for navigation between scatterplots. In particular, we have introduced an animation method that supports transitions between 3D scatterplots that are perceived as 3D rigid body rotations. We have shown how our transition scheme nicely fits to navigation with 3D scatterplot matrices. Our technique has the benefit of preserving context by navigating between different 3D scatterplots. 1976. Figure 3. Scatterplot matrix navigation, showing how the 3 clusters of the olive oil dataset can be separated. We start with a 3D scatterplot in which the dimensions palmitic 0, palmitoleic 1, and stearic 2 are mapped to the x, y, and z axes respectively, subfigure 1. The 3 clusters are not separated in the scatterplot. In the 3D scatterplot matrix, we see that the dimension ecosenoic 7 separates the red cluster from the other. 2. We choose to map this to the x-axis, subfigure 2. The scatterplot is rotated to the subspace where the transition that replaces dimension 0 by. Dimension 7 will appear as a rigid body rotation, subfigure 3. The transition is shown in subfigures 4 to 7. By now, the red cluster is clearly separated and mapped to the x-axis of the scatterplot, and we can try to separate the green and blue clusters using the other 2 axes. We now rotate the 3D scatterplot to show the y and z axes. From the 3D scatterplot matrix, we see that arachitic 6 and linoleic 4 separate the 2 clusters, subfigure 8. We choose to map these to the y and z axes respectively, subfigure 9. We rotate to the subspace where the transition that replaces dimensions 1 and 2 by dimensions 6 and 4 will appear as a rigid body rotation, subfigure 10. The transition is shown in subfigures 11 to 14. At the end of the transition, the clusters are also separated in the projection. Subfigures 14 to 15 give an impression of the 3 locations of the points. The dimensions, ecosenoic, linoleic, and arachitic, have been identified to separate the 3 regions. Instead of just switching between them, it provides a way for the user to easily follow the rigid body motion of the points of the scatterplot, heavily reducing the cognitive load that would be associated with the unconstrained animation of data points between scatterplots. We have shown in a controlled user study that rigid body rotational transitions are more effective than interpolating transitions. The usefulness of our 3D scatterplot navigation approach is largely subject to the degree of usefulness and appropriateness of single 3D scatterplots. The utility of 3D scatterplots compared to 2D scatterplots can suffer badly from inaccuracies due to perspective projection and from ill-designed rendering that would fail to support depth. perception from static views and rely only on structure from motion. Since 3D scatterplots without additional depth, cues look like 2D scatterplots when viewed along the major. They'll only provide additional information when they are extended with depth cues but have no drawbacks from such. 1977. Acknowledgements. This project was supported by the DFG Collaborative Research Center /SFB 627, Nexus. R references 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, Figure 4. Comparison of 2 and 3 axes mappings and 1 rotational degree of freedom. In the upper 2 images, the horizontal and vertical image axes show the same data dimensions, length underscore squared and intersect, time underscore count, respectively. There is no depth axis used in the upper image. In the center image, data dimension norm underscore distance is assigned to the depth axis. Halos emphasizes the variation with respect to norm underscore distance. In the data, the lower image uses the same axis mapping as the center image and shows the data set from above. Static viewpoints. For application areas where emphasizes the variation with respect to norm underscore distance. In the data, the lower image uses the same axis mapping as the center image and shows the data set from above. Static viewpoints. For application areas where interactive 3D scatterplots are useful, the enhancement by 3D scatterplot navigation will be useful as well. In addition, there are facts and shows the data as visualization, pages 130, E. Retzel and P. Berry. Flexible information visualization of multivariate data from biological sequence similarity searches, Proc 7th Conference. Visualization, pages 133 to 140, 1996. D. Cook, D. Corrija, and V. Honavar. Visualization in classification problems with examples using support vector. Machines, Proc. Computational Statistics, pages 799 to 806, 2004. T. N. Dang, L. Wilkinson, and A. Anand, Stacking Graphic Elements to Avoid Overplotting, IEEE Trans. Visualization and Computer Graphics, Volume 16, Number 6, pages 1044 to 1052, November/December 2010. A. W. Donahoe, D. L. Donahoe, and M. Gasco. Maxpin, Dynamic Graphics on a Desktop Computer, IEEE Computer Graphics and Applications, Volume 8, Number 4, pages 51 to 58, July 1988. N. Elmqvist, P. Dragicevic, and J. D. Fekete. Rolling the Dice. Multidimensional Visual Exploration Using Scatterplot Matrix. Navigation, IEEE Trans. Visualization and Computer Graphics. Volume 14, Number 6, pages 1141 to 1148, November to December 2008. M. A. Fischerkeller, J. H. Friedman, and J. W. Tukey. Prim 9, and Interactive Multidimensional Data Display and Analysis System. Proc. Pacific ACM Regional Conference, 1974. M. Forina, C. Armanino, S. Lanteri, and E. Tiscornia, Classifica. 10 of olive oils from their fatty acid composition. Food. Research and Data Analysis, H. Martins and H. Roosvoorm, eds. Pages 189 to 214, Applied Science Publishers, 1983. K. R. Gabriel, The Biplot Graphic Display of Matrices with Application to Principal Component Analysis, Biometrica, Volume 58. Number 3, pages 453 to 467, 1971. J. Hare and G. Robertson, Animated Transitions in Statistical Data Graphics, IEEE Trans. Visualization and Computer Graphics, Volume 13, Number 6, pages 1240 to 1247, November/December 2007. R. Kosura, G. N. Salling, and H. Hauser. Linking Scientific and Information Visualization with Interactive 3D Scatterplots. Proc 12th International Conference Central Europe on Computer Graphics Visualization and Computer Vision, WSCG, pages 133 to 140, 2004. J. A. Nelder and R. W. M. Wedderburn, Generalized Linear Models. J. Royal Statistical Soak. Series A General, Volume 135, Number 3, pages 370 to 384, 1972. H. Piringer, R. Kosera, and H. Hauser, Interactive Focus plus Context. Visualization with linked 2D/3D scatterplots, Proc International Conference. Coordinated in Multiple Views and Exploratory Visualization, pages 49 to 60, 2004. J. Poco, R. Etimidpour, F. Paulovich, T. Long, P. Rosenthal, M. Oliveira, L. Linson, and R. Mingham, A Framework for Exploring Multidimensional Data with 3D Projections, Computer Graphics. Forum, Volume 30, Number 3, pages 1111 to 1120, 2011. Z. W. Pilishin and R. W. Storm, Tracking Multiple Independent Targets, Evidence for a Parallel Tracking Mechanism. Spatial Vision, Volume 3, Number 3, 179 to 197, 1988. H. Sanftmann and D. Weiskopf, Illuminated 3D Scatterplots. Computer Graphics Forum, Volume 28, Number 3, pp. 751 to 758, 2009. C. Stolt, D. Tang, and P. Hanrahan. Polaris, a system for query, analysis, and visualization of multidimensional RELA. Chanel databases, IEEE Trans. Visualization and Computer Graphics, Volume 8, Number 1, pages 52 to 65, January to March 2002. D. F. Swain, D. Cook, and A. Buja. Zgobi, Interactive Dynamic Data Visualization in the X-Window System, J. Computational and Graphical Statistics, Volume 7, Number 1, pages 113 to 130, 1998. D. F. Swain, D. T. Lang, A. Buja, and D. Cook. Gobi, Evolving from Zgobi into an Extensible Framework for Interactive Data Visualization, Computational Statistics and Data Analysis, Volume 43, Number 4, pages 423 to 444, 2003.1978. 22. M. Tarini, P. Signoni, and C. Montani, Ambient Occlusion and Edge Queuing for Enhancing Real-Time Molecular Visualization. IEEE Trans. Visualization and Computer Graphics, Volume 12, Number 5, pages 1237 to 1244, September/October 2006. 23. J. Todd, The Visual Perception of 3D Shape, Trends in Cognitive Sciences, Volume 8, Number 3, pages 115 to 121, 2004. 24. M. Torrey, Mental Registration of 2D and 3D Visualizations. Empirical Study, Proc IEEE Conference Visualization, pages 371 to 378. 2003. 25. B. Tversky, J. B. Morrison, and M. Betrancourt. Animation, Can It Facilitate? International J. Human Computer Studies, Volume 57, Number 4, pages 247, 262, 2002. 26. S. Ullman, The Interpretation of Structure from Motion, Proc Royal Soc London B, Volume 203, pages 405 to 426, 1979. 27. M. Ward, XMDV Tool, Integrating Multiple Methods for Visualize. Ing. Multivariate Data, Proc IEEE Conference Visualization, pages 326 to 333, 1994. 28. C. Ware, Visual Thinking for Design. Morgan Kaufman, 2008. 29. L. Yang, 3D Grand Tour for Multidimensional Data and Clusters. Proc Simp. Advances in Intelligent Data Analysis, pages 173 to 184, 1999. Harald Sanftmann received the Diplom MSc degree in computer science from the University of Stuttgart, Germany. From 2005 to 2008, he worked as a software developer for Harman / Becker Automotive Systems GmbH, Karlsbad, Germany. Since 2008, he is a scientific assistant at the Visualization Research Center, University of Stuttgart, VISUS. His research interests include multivariate data visualization and perception-oriented computer graphics. He is a student member of the IEEE. Daniel Weiskopf received the Diplom MSc and the Dr. Nat PhD degrees in physics, both from the University of Tübingen, Germany, and the habilitation degree in computer science from the University of Stuttgart, Germany. From 2005 to 2007, he was an assistant professor of computing science at Simon Fraser University, Canada. Since 2007, he has been a professor of computer science at the Visualization Research, the University of Stuttgart, VISUS, and at the Visualization and Interactive Systems Institute, VIS, University of Stuttgart. His research interests include visualization, visual analytics, GPU methods, real-time computer graphics, ubiquitous visualization, perception-oriented computer graphics, and special and general relativity. He is a member of the ACMC Graph, the Gesellschaft for Informatik, and the IEEE Computer Society. For more information on this or any other computing topic, please visit our digital library at www.computer.org/publications/lib. 3D Scatterplot Navigation. Harald Sanftmann, student member, IEEE, and Daniel Weiskopf, member, IEEE Computer Society Abstract, for 3